The next three chapters of this course deal with the second law of thermodynamics. Chapter 5, roughly, we can say it involves two subjects. The first topic, we are going to introduce what is second law of thermodynamics in a qualitative way. And we are going to use heat engine and heat pumps are the primary examples. Then we're going to look at some characteristics of second law. We're going to look at the second law from different aspects. Now quickly review what we have discussed about heat engine and the heat pump. As we discussed earlier, heat engines are machines involve cyclic fluid, which the cyclic fluid absorb heat at a high temperature. Then it will do some work in turbines and then release the residual heat to the low temperature reservoir before it returns to the high energy source. A heat pump is like refrigerators, air conditioners. The working fluid also runs in a cyclic process. It absorbs energy at a low temperature and then release the energy to the high temperature environment. In this case, we have to do some work to the refrigerator or air conditioner. If we look the heat engine closely, it involves 4 unit operations. Usually, the working fluid absorbs the heat in the high temperature reservoir. It does work, and a part of the work is used later on to pump the fluid back to the heat source. The residual heat is released to the low temperature environment. If we look at the 4 unit operation like this, and then just draw this rectangular box as the heat engine, then we can simplify the work and the heat terms in this way. The working fluid absorbs the heat from high temperature, release the heat at a low temperature, and it does useful work. And this useful work involves the work which is used to pump the fluid back to the boiler. And notice one thing, which is maybe different from what we have discussed in the last 2 chapters. All the terms in these diagrams are positive. Some textbooks use absolute value signs for these terms, but this textbook doesn't. So be aware, this is slightly different from what we've been discussing in the last 2 chapters. All these 3 quantities are positive. Then we applied the energy balance. We said the work is essentially the difference between the 2 energy transfer terms. Then we can define a very important term which will be used many times in a subsequent discussion. That is thermal efficiency. Thermal efficiency is designated by eta, and it comes from this definition. Imagine as an investor, if we want to build a power plant, we would like to generate as much work as possible based on burning certain amount of fuels. So this is an important quantity as an engineer or as an investor. We would like to have this number as high as possible. If we replace this W term by the difference of the two Q term, we get this ratio. And this ratio, of course, can be simplified to 1 minus QL divided by QH. And if we want the thermal efficiency as high as possible, we can tell this ratio has to be as low as possible. QL to QH has to be as low as possible. And usually this eta is between 0 and 1. If we got a number higher than 1, that's impossible. And here is an example. We're going to use the automobile engine as an illustration. The automobile generate 136 horsepower for the car to move forward. And if we know this car has a thermal efficiency 30%, so that means this number 136 horsepower is only 1/3, roughly 30% of the energy produced from burning fuels and provided to the working fluid. The working fluid in this case will be air and the fuel as a whole. And if we know the fuel burns and release 35,000 kilojoules per kilograms of energy, that's QH dot. Then we are asked to find out how much heat is released to the low temperature reservoir. So essentially, we are asked to practice the first law, the difference of the two Q terms is the useful work produced. And we are already given the useful work provided by this heat engine, 136 horsepower. We have to convert this unit to kilowatts. Notice this is a conversion unit between horsepower and the kilowatts. And then we use the definition of thermal efficiency. We can estimate the total energy provided by the high temperature reservoir. That's this number divided by 30%. Then we can figure out the QL term. And finally, the rate of heat transfer at high temperature equal to the mass flow rate times the Q sub h, the lowercase q. By using this equation, we can calculate the mass flow rate. If we look at what we have learned about the heat pump before, the working fluid passing through the valve, it expands. It expands so large, so the liquid evaporates. When the liquid evaporates, it absorbs the heat. So this is what happens inside our refrigerator or air-conditioned room. It absorbs the heat when the working fluid evaporates. Then the compressor will have to pump the cold vapor to outside the air conditioner or the refrigerator to release the heat. So this completes a cyclic process. And this is the simplified diagram of a refrigerator. We have to do the work in order to make it happen. So the working fluid absorbs the heat. That's the QL term. It releases the heat to high temperature environment. So it's a Q dot term, QH dot term. And the energy balance yield this equation, the work required for this process to take place is the difference of the two Q terms. Notice again, in this diagram, also in this equation, all these three terms are positive. Then we define two important quantities related to refrigerators. The first one is called efficient of performance, or COP. There are two types of COPs. One is related to the air conditioner heat transfer to the work. Again, as a investor, to make the refrigerator, we are concerned about the COP. COP is defined as how much heat can be removed from the air conditioner divided by the work provided to the refrigerator. This work is provided by the electricity. So that means how much heat can be removed from the refrigerator versus the consumption of electrical energy. And if we replace this W term, we get this expression. And the second COP is defined as the total energy released to the environment divided by the energy, electrical energy provided to the unit, to the refrigerator. Again, if we replace this term by the energy balance equation, we get this expression. The only difference between these two COPs is the numerator. One is referred as QL dot term, and the COP is designated with a subscript, REF, denoting refrigerator. And for the second COP, the numerator is QH dot. And the COP is designated by a subscript heat pump, HP. And the two COP have the relation, they have to be differed by 1. And then if we look at this example, if this is a refrigerator, and if we know to keep the refrigerator running, we need to have 150 watts of power. And if we know it reject 400 watts of energy to the high temperature reservoir, we are asked to find out the QL term and the COP related to the refrigerator. So to answer the first question, we use the energy balance equation. QL is the difference of W term and the QH dot term. And the COP of a refrigerator, by definition, is QL divided by W, the work provided to the refrigerator. So this is another example. Then we have to introduce you to two different forms of second law as a beginning statements. These two statements stated in the middle of the slide are the two commonly observed phenomena. No one has observed differently. The first one starts with Kelvin Planck for heat engine. It says it's impossible to convert the energy completely to work. The second statement is was initiated by Clausius for heat pump. It says it's impossible to bring the heat, 100% of the heat, from low temperature reservoir to high temperature reservoir without work. So these are the two commonly observed phenomena. Mathematically, we can say the energy balance equation, if we look at the energy equation, if we start with the energy balance equation we have seen before, and then look at the efficiency. We know the efficiency has to be between 0 and 1. It cannot be even 1. And then if we look at the Clausius statement for pumps, heat pump, we see that we must have a W term greater than 0 in order to run the air conditioner or refrigerator. Then we have this equation for the refrigerator, and the beta term is always between 0 and infinity. And these two statements are actually equivalent. By looking at this figure, if we combine a heat pump and a heat engine, and if we draw this dashed box as the control volume, and if we said the Clausius statement is no longer true, so we can run the system without work, then what happens is we're going to have this equation W equal to QH minus QL, and without W, that means W20 is 0. That means we can bring heat from low temperature reservoir to high temperature reservoir. These two terms, Q terms, are equivalent. It's impossible. So that this statement violates the Kelvin-Planck statement. Therefore, these two statements, Clausius statement and the Kelvin-Planck statement, are essentially equivalent.